How's it going? My name is Micah Fagerstrom.
I'm Renee Yock.
We are doing a project for our electrochemical engineering class. We'll be presenting our fuel cell analysis of varying anode and cathode channel geometries. So this is kind of the agenda that we're going to follow today. We're going to start off with our introduction and objective, and we're going to go into our experimental components and the variables that we use to simulate our data. We're going to go over our procedure that we took, the results, conclusions, and then we'll wrap it up with our references.
Okay, so a bit of introduction to the experiment. Of course, in today's day and age, fuel cells are very important. We need them to power a lot of our appliances back home. So for engineers, one of their experiments are for improving fuel cells. This involves changing the geometries of the anode and cathode channels to improve hydrogen flow, as well as in this experiment, we're going to be analyzing how the flow rate changes throughout the channels.
So the objective of our experiment, we had a couple. One of the biggest ones was to see the relationship between the flow channels based on the geometry, shape, and size. We took the geometry from homework 6, which was a square. Then we went with a smaller square, half circle, and a triangle, and we analyzed those geometries against each other. We also wanted to see how the current flow varies between the channels. And we also wanted to learn more about ANSYS Fluent and how to navigate through that program better.
So in ANSYS Fluent, we made the mesh and we imported it into ANSYS Fluent to do the simulation. On right here, you can see the standard layout that we use for the fuel cells. We have the two gas channels on the top and bottom. We have the cathode gas diffusion layer as well as the anode gas diffusion layer. We have the two catalyst layers and the electrolyte membrane in the middle. Just like we did in homework 6, we kept these variables consistent with our simulation. We have the saturation source as 0.1, the water content as 0.06, current density as 7,500 amps per meter squared, the open circuit voltage at 0.95 volts, and the temperature at 353 Kelvin.
So the procedure we took, we had to make the shapes. So here's the meshes that we took right here. This one was the one in the lab procedure, the square. It might be hard to see, but we also have the semicircle, the triangle, and the little square. And then along with making the meshes, we had to enter the same parameters from homework 6 in that lab manual. The reason we wanted to have the same parameters was so we can compare our results against each other. If we changed something like current density, then we couldn't really make an accurate decision of what channel is the best for our flow. Then on top of that, we did find the current density flow, which we will talk about, and we made mass contour plots of the mass fractions, and then we were able to draw conclusions. This is a schematic that we follow, which is pretty standard in ANSYS Fluent.
So for our results, here the pictures represent the square, the half circle, triangle, and the little square geometries that we did in ANSYS. We have the flow of hydrogen from left to right, which seems to be consistent for all the geometries. We notice that as the size of the channel increases, the mass fraction increases as well throughout the channels. We also noticed that for the oxygen channel, the results were flipped, and which is something that we expected for our results.
And then also for the current density flow, here's the plot from the lab manual, and then here's the one we did for the triangle. Based on the way ANSYS works, it's kind of difficult to get a good view for our triangle, so that's why we have an isometric view. However, we did notice that the maximum current density does occur between the channels for all of them. You can see that here, most of the current density flow is right in the middle, and same here. So after seeing that, we determined that we couldn't use that to decide our optimal flow channel. So we ended up using the contour plots as our deciding factor.
So in conclusion, we found that the large square was the best shape to have for our geometries. It had the largest mass fraction, and we also noticed that the bigger the shape is of the channels and the less sharp edges, the better. However, we also noticed that it's a trade-off depending on the geometries. So ultimately, engineers had to find the best geometry for their fuel cells to optimize the performance. We found out that current density flow is similar throughout the channels regardless of the geometries. Some improvements that we would have done to this project were to analyze more shapes in the channels, as well as maybe increase the size overall to see how mass fractions would change throughout the channels.
Here's the references we use. This is one that gives a little bit more information about fuel cells, and then we use the homework 6 lab manual. That's our presentation today. Go ahead, if you have any questions, drop a comment below and we'll try to answer that. And then otherwise, just go ahead and subscribe. I currently have 0 subscribers, so that'd be beneficial. Thank you.
Thank you.